In last class, we have seen some introduction to hypothesis testing, and we have seen one-tailed test and two-tailed test. Today, we will see statistical significance. To understand statistical significance, let's take one example. Suppose you are trying to decide whether a coin is fair or biased. Here, null hypothesis is coin is fair, alternate hypothesis is coin is biased. To decide that, if we toss a coin, how often it will come up heads. If coin is fair, half of the times it will result heads. So we can write our null and alternate hypothesis in this way also. H0 probability of heads will be 0.5 and alternate hypothesis is probability of heads not equal to 0.5. I have just tried 10 tosses and got heads 6 times, which proves that coin comes up heads 60% of times, but my result stands away from this null hypothesis 50. This small variation is acceptable because we did not toss coin more times. If you toss coin suppose 1000 times, it might be close to 50%. So this is likely result for fair coin. But if I observe 8 heads in 10 tosses, here difference is more, means actual for fair coin 5 heads and 5 tails should be there, but here we observe 8. The difference here is more. This much big variation is not possible if I toss fair coin. So this is unlikely result for fair coin. Here, to decide coin as biased, we need to estimate how unlikely our observed results are with respect to fair coin. If it is very unlikely, this difference is more. So this much big difference not considered as a random chance. We can decide the coin as biased. If this difference is small, that might be considered as a random chance and that coin as fair coin. You would reject null hypothesis in favor of alternate hypothesis if observed number of heads difference is huge from 5. How to decide the difference is big or small? We need some cutoff criteria, like if observed number of heads less than 2, you can consider that difference as big, and even if a number of heads greater than 8, the difference is more. If you have some observations which are 6, 4, 5, 7, the difference from the 5 will be small, so you will consider this difference as small. Observations in statistical study is said to be statistically significant if it is unlikely to have occurred by a random chance. Means if result is not by random chance, you call the result as statistically significant result. So in statistical significance, we need to determine how unlikely an outcome was to occur by a random chance, and then decide if the probability is unlikely enough. We can conclude something other than the random chance caused the outcome. Let's take another example. You try to determine if the health drink makes the children gain height. To test that, study was conducted. 100 children were selected for study. You need some standard to compare the study results. Suppose average height of 5-year children is 100 centimeters with standard deviation 2 centimeters in normal conditions. It means they didn't use any special food or any medication. Health drink was given daily for these 100 children. Assume except this health drink, other conditions are same, means they have same food as the children within this study. And you measure this test group 100 children's average height when their age is 5 years. If you find the children who took the health drink gained more height than this 100 centimeters, does that mean health drink caused the increase in height gain? For instance, maybe the health drink is the factor for change in results, or maybe the change in results is just a random chance. Even if you give the same food, like you don't give any health drink, and if you try to measure the average height, there will be some variation from that 100 centimeters. That variation is called a random variation. It is caused due to some random chance, not because of that particular health drink. Statistical significance is a way of determining which of these possibilities is true. Height is not dependent on the health drink. Change in results is just random variation. Height is dependent on health drink. Change in results is not random variation. Really, it is because of health drink. Here, null hypothesis is the test group mean height, this mu, is same as 100 centimeters, which is standard mu naught. And alternate hypothesis mu naught equal to 100 means they have some different mean height which is not equal to this 100 centimeters. If it is not equal to 100 centimeters, health drink is the reason for this difference. We need to determine how unlikely an outcome was to occur by random chance in this null hypothesis, and then decide if the probability is unlikely enough in null hypothesis. We can conclude that the health drink is the factor. Let's assume this one has null distribution and this one has alternate distribution. Null distribution is the probability distribution of test statistic when this null hypothesis is true. If you take this null distribution, mean of null hypothesis is 100 and standard deviation is 2. So, two standard deviations will be at 104 and 96. Within these two standard deviations, 95% of observations will be covered. 5% of observations may fall outside these two standard deviations in this red region. The values which are in this red region are unlikely in this null distribution. Suppose mean height of test group is 110 centimeters, which is falling in this red region, means outside of 95% confidence interval range of this null distribution. This observation is unlikely in this null distribution. This is very likely within this alternate distribution. So this value is significant in favor of this alternate hypothesis. The values which are within two standard deviations are likely in this null distribution. Suppose if the test group mean is 1 or 2 centimeters, then it will be within the two standard deviations. This value is very likely within this null distribution. This value is not significant in favor of this alternate hypothesis. If we calculate difference between mean scores, if the difference is large enough, the results are significant in favor of alternate hypothesis. If we take the first case, test group mean is 110, then difference from the null hypothesis mean is huge, so these results are significant in favor of the alternate hypothesis. If you take the probability value of this 110 within this null hypothesis, it is very small. If probability is small, then you call that observation as significant in favor of alternate hypothesis. If we take the another case, if test group mean is 1 or 2, the difference from null hypothesis mean is small, so this value is not significant in favor of this alternate hypothesis. If you take the probability of observing this value within this null hypothesis, this probability will be more because which is close to this mean. So if probability is more, the results are not significant in favor of this alternate hypothesis. In hypothesis testing, we are interested in proving this alternate hypothesis, but to test the validity of this alternate hypothesis, we will use this null hypothesis. If it fails, then you will consider this alternate hypothesis as valid. So we will check whether this results in favor of this alternate hypothesis, the theory which we want to prove. If these results are significant in favor of this alternate hypothesis, we will reject this null hypothesis. Let's see how the statistical significance used in hypothesis testing. Hypothesis test can have one of two outcomes. One is null hypothesis is rejected and alternate hypothesis accepted. And second one, null hypothesis is not rejected based on evidence. Statistical significance is used to determine whether null hypothesis should be rejected or not based on evidence. We already know that statistical significance helps us that change due to random chance or due to some factor like health drink in our previous example. In our previous example, we assumed that 5-year children average height supposed to be 100 centimeters with standard deviation 2. This 100 is standard, let's say mu naught. We need to find whether the average height of this test group children who were given health drink different from this 100 centimeters. For this statement, if we form our null and alternate hypothesis, here null hypothesis H naught mu equal to 100. This 100 is research standard, so let's call it as mu naught. This null hypothesis means the average height of test group is same as the standard mu naught. Here it is 100. Here null hypothesis is not claiming any difference from this research standard. Here this mu is the estimated population mean for test group. It will be same as mu naught in null hypothesis. Means this mu equal to mu naught. Alternate hypothesis H1 mu not equal to 100 means average height of this test group is different from this standard mu naught. It is 100 here. If this test group mean value falls outside 95% confidence interval of this null hypothesis, then we will say results are significant. Change is really due to health drink if result falls in this red region. If test group mean value falls within this 95% confidence interval of null hypothesis, results are not significant. This change from this mean value is due to random chance. It is not because of health drink. Here 95% confidence interval means all the values within the two standard deviations from the mean. We assume that 5-year children average height will be 100 centimeters with standard deviation 2 centimeters. So the value at 2 standard deviations will be at 104 and lower bound will be 96. But in statistic, usually instead of this original distribution, standard normal distribution will be used. All these scores will be converted into standard normal scores or Z scores. Then we can reject null hypothesis when results are significant. Results significant means these results are supporting alternate hypothesis. That is the theory actually we are trying to prove. Means the children who drink the health drink height is not same as this other group. Means results are very unlikely in this null hypothesis, or these results are too far from the expected mean. Expected mean here it is 100. It will be 0 in standard normal distribution. The observed results will be too far from this mean value. This red region is too far from the mean 0 when compared with the values within this blue region, sky blue. We can check whether the results are statistically significant or not in two ways. One way is based on confidence interval critical regions. If observed value does not falls in the pre-specified confidence interval region, we can say that null hypothesis is very unlikely. Here if results fall outside this confidence interval, these two are the critical values, 2 standard deviations away. Observed value falls within these two regions, then we will say that these values are very unlikely for null hypothesis. So results are statistically significant in support to the alternate hypothesis. And second way is based on p-values. If observed p-value is less than pre-specified significance level alpha, results are statistically significant. Suppose test group mean score is 1 or 2, this one, and standard deviation is 2. Convert this 1 or 2 into Z score. It will be 1 somewhere here. This is observed Z value. In standard normal distribution, 95% confidence interval, Z scores are minus 1.96 and upper bound value is 1.96, and calculated Z statistic is 1. It will be fall somewhere here, this blue line. To reject null hypothesis, result has to be significant. Here 1 is between this minus 1.96 to 1.96, 95% confidence interval boundaries. So results are not statistically significant. If results fall outside this region, then we can say that results are significant in support to the alternate hypothesis. But here the results within the confidence interval range, so null hypothesis cannot be rejected. Means these results are very likely to happen within the null hypothesis. We can test same thing in other way also by using p-values. Let's see that. But we don't know what p-value is. Let's see the p-value first. P-value is the probability value of obtaining results at least as extreme as the observed results of statistical hypothesis test, assuming null hypothesis is true. Means if our calculated Z value, suppose 1, this is our Z value, then you have to take the probability value or P value from this Z to this extreme value. If it is in left tail, if you observe Z statistic as 1.5, from this 1.5 to this extreme left end, this area in this tail is called as p-value. So p-value is frequently called as the tail probability. P-value is measure of the probability that an observed difference could have occurred just by a random chance. Lower p-value, greater the statistical significance. Means if your results are very extreme, then if you calculate the area after this value, this probability value will be very less, so results are significant. Let's see how to calculate p-values for known Z value. This p-value calculation will be different for one tail test and two tail test. If left tail test, we will calculate in some way. For right tail test it will be different, and for even two tail test it will be different. So let's see how this will be calculated for these three different tests. If rejection region is in the left tail, then we call that test as a left tail test, and if rejection region in right side, we call that test right tail test. If rejection region both of the sides, right tail and left tail, then we call that test as two tail test. Let's see, for calculating p-value for left tail test, if our Z value is minus 2.25, means in Z table we will contain the cumulative probabilities from minus infinity to up to this Z value. So anyway, p-value means from this Z value we need to calculate the total area to the extreme. Here it is left tail test, so till minus infinity. Anyway, cumulative probabilities in Z table will be from minus infinity to Z. So for p-value calculation in left tail test will be easy. You have to see the value at this Z score in Z table. Let's see Z score for this minus 2.25 in Z table. Z score is minus 2.2 and 5. This will be the cumulative probability. So we can take that cumulative probability directly as a p-value in left tail test. So p-value here it is 0.01222. So this is the p-value for Z value minus 2.25 in left tail test. Let's see for the calculation of p-value in right tail test. If our Z value is 1.5, but here p-value will be from this 1.5 to this end, but cumulative probabilities in Z table will start from minus infinity to this Z value. So see the value for this Z score and subtract that value from the 1, means entire area under this curve will be 1. We will get the p-value. Let's see the cumulative probability at this 1.5. This is the Z score 1.5. So cumulative probability 0.93319. This is probability value from this minus infinity to up to here, this region. But we want this region p-value, probability value. So subtract this value 0.9331 from the entire probability, that is 1 in the standard normal distribution. So you will get the p-value in the right tail, that is 0.0668. This is the p-value for this Z 1.5 in right tail. Let's see how to calculate p-value in, it is not right tail, two-tail test. If a Z value is 1, then you need to calculate probability from this Z value to extreme. Here it is plus infinity. Instead of just calculating this from this minus 1 also, same probability will be there because the standard normal distribution is symmetric. So see the cumulative probability for minus 1. Actually these tables are big, so I just given the sum portion of these tables. Here we don't have minus 1 value. Let's see this Z score plus 1. Here 1 is there, but it is the cumulative probability from minus infinity to this score 1. So you have to subtract this cumulative probability from the 1. This value is 0.84134. So 1 minus 0.841. If you subtract that, you will get value 0.158. Because it is two-tail test, rejection region will be both sides. So just multiply this value with 2. You will get the p-value for this two-tail test. The result here it is 0.3173. For left tail test, you can take the cumulative probability directly. For right tail test, you take the cumulative probability from minus infinity to up to this Z value, and you have to subtract it from the 1. You will get the p-value for right tail test. And for two-tail test, take the probability in any one of the tail and multiply it with 2. You will get the p-value for two-tail test. Now let's check whether we can reject this null hypothesis or not based on p-value. We calculated the Z value, it is 1. Let's check the p-value for this Z statistic 1. Here it is two-tail test. We already calculated p-value for two-tail test where Z equal to 1. This is the p-value for two-tail test at Z equal to 1. 95% confidence level means alpha will be 0.05. In two-tail test it will be distributed 0.025 in right tail and 0.025 in left tail. But when we are using this second method, p-values, to reject null hypothesis or not, we will compare this p-value with the entire alpha value. So just sum these two values and use this alpha to compare with this p. So our p-value is 0.318 and alpha value is 0.05. This p-value actually greater than this alpha value. If p-value less than alpha value, then results are significant, but here p-value not less than alpha value, so results are not significant. So we cannot reject null hypothesis. Let's see other case. Suppose test group mean score is 110 centimeters instead of this 1 or 2. We will check whether this score is significant or not. Convert this 110 centimeters into Z score. 110 minus mu is 100 by standard deviation is 2. Then it is 10 by 2. It is 5. So Z statistic value is 5. It will be somewhere here on the graph. It is not in the confidence interval of 95% from minus 1.96 to 1.96. Results are statistically significant. So null hypothesis can be rejected. Let's check by using p-value for this mean value of 110. We need to find the p-value at Z5. Here this table is not covered this all values. So see here up to z score 2.3, probability value is 0.99158, means it will be more than that. If you check the value cumulative probability, if you check the cumulative probability at z5, it will be 0.99997, because this probability from minus infinity to up to this z, so you have to subtract this value from 1, then you will get p value 0.0000003. because it is two-tailed test, you have to multiply it with 2, then you will get the p value for z5 in two-tailed test will be 0.000006. This is the p value. You have to compare this p value with the alpha. If you take 95% confidence level, alpha will be 0.05. This p value 0.6076 is less than this 0.05. because p value less than alpha, results are significant. So results are significant. Here it is written as can't reject, so it is not right. We can reject the null hypothesis. P value is the probability value from that z to extreme. So if z value is far from the mean, then that probability under that curve will be less. So that kind of results are in support with the alternate hypothesis instead of supporting this null hypothesis. So if p value less than your significance level alpha, you will say that null hypothesis is not correct. Small p values try to support the alternate hypothesis. Means if p value less, it is supporting for the alternate hypothesis, so you will reject the null hypothesis. It would be incorrect to conclude that null hypothesis is not rejected. It can be accepted as valid. If you are unable to reject this null hypothesis, we cannot accept it as a valid. To understand this, let's assume hypothesis is all swans are white. To prove this, we have to check color of all swans in the world. If you find all are in white color, then only you can accept it. Means you need to test entire population. But rejection is easy. If you find single different colored swan, like suppose some black color swan, if you find based on this single black colored swan, you can say that all swans are not white. Here we are taking sample, not considering entire population. So you cannot accept null hypothesis, but you can reject based on evidence. In order to accept this null hypothesis, you have to search for entire population. But for rejection, if you find a single different colored swan, then you can reject. This hypothesis testing will be based on only sample. So we can never say that null hypothesis is accepted. Instead that we will say that null hypothesis cannot be rejected based on evidence.